Hi and welcome to Prototype. We'll be solving the problem for LeetCode 509, Fibonacci number. This is another problem in the LeetCode 75 study plan. Let's get to it. So the Fibonacci numbers, commonly denoted f of n, form a sequence called the Fibonacci sequence, such that each number is the sum of the two preceding ones starting from 0 and 1. And they give two base cases, so f of 0 is equal to 0 and f of 1 is equal to 1, and then they give a formula. F of n can be described by the sum of f of n minus 1 plus f of n minus 2 for n greater than 1, and it wants us to calculate f of n when we're given n. Okay, the first example, n is equal to 2, f of 2 is equal to f of n minus 1, which is 1, and f of 2 minus 2, which is 0. And we have the base cases already, so f of 2 is equal to 1 plus 0, or 1. All right, so the Fibonacci number is the typical intro to dynamic programming problem. And in fact, they already give you the recurrence relation right in the description. And the recurrence relation is simply a formula that defines the next term in a sequence by the previous term or previous terms. In this case, f of n is equal to f of n minus 1 plus f of n minus 2. All right. The simplest solution would be to use recursion. And normally recursion can be a little difficult to wrap your head around because you need to find the recurrence relation. But in this case, it's given to us, so the recursive solution is very easy. We can just say, have the base cases, so if n is equal to 0 or n is equal to 1, then we know we can just return n, because in either of those cases, n equal to 0, f of n is equal to 0, and 1 is 1. Okay. Otherwise, we're going to return the recurrence relation. So fib of n minus 1 plus fib of n minus 2. And that's it. Can just run it. And this works all good and well for small cases of n, but actually this is a very slow and in fact very space inefficient algorithm as it stands, because the time complexity is 2 to the power of n, and also it will be filling the call stack exponentially as well. Why? Because for every n greater than 1, so even f of 2, each fib call, so the fib call for f of 2 needs to call fib twice, right? So fib of 2 is fib of 2 minus 1 plus fib of 2 minus 2. And to illustrate this, we can just think of fib of 5. Okay, so if we want to calculate fib of 5, we would need to calculate fib of 4 plus fib of 3. But to calculate fib of 4, we need to calculate fib of 3 again, and then fib of 2, right? And then we keep going and going. So even just with 2 iterations, you could say, or 2 calls within the original call, we've already had to calculate fib of 3 twice. Okay, so that's why it's so slow. But of course, because the work is duplicated, we can vastly improve the solution just by keeping stored work. And how can we do that? Well, we can just use a array. Let's just call it dp, and we'll fill it with 0 and 1, and this will reflect the base cases. So again, when n is 0, so we can use the array index, right? If n is 0, then dp of n is 0, and when n is 1, then dp of n is also 1. And then otherwise, we'll be filling the array with each calculation. Okay, so let's have one more function. Let's call it, let's just call it recursion. And it will also be n. And the first thing we'll be checking is if dp of n exists. And actually, we should check if it's not null, because 0 is a falsy value in JavaScript. Then we return dp of n. So essentially, if we've already calculated f of 3, then just return f of 3. There's no reason to calculate f of 3 again. Otherwise, then we need to fill the array. So dp of n is equal to recursion n minus 1 plus recursion n minus 2. Okay, and once it's calculated, then we return dp of n. And then we just modify our bottom to say we return recursion n. Okay, let's run that. Okay, and submit. And so apparently that beats 81%. Okay, so what have we done? We've just added an array or a storage mechanism, you could say, to store the work as we're working towards the solution, as we're working to calculate. So when we calculate, let's say f of 5, then once we calculate f of 4 and then f of 3, we save them and we don't recalculate them. Okay. What is the next step? Iterative solution. Let's do that. So in the iterative solution, we can keep our dp array to start, and let's use a for loop. So for let I equal to 2, and we're going to start at 2 because we already have I equal to 0 or I is equal to 1, right? I less than or equal to n, I plus plus. Then what are we doing? We'll be filling our array as we go along. So dp of I is equal to dp of I minus 1 plus dp of I minus 2. Okay. And just give me 1 second to go plug in my MacBook, actually. Okay, sorry about that. Okay, and then after that, then we return dp of n. So all that's happening here in this case is we're going to start from, you could say n is equal to 0 even, really, because we filled in our base case. But okay, so starting from 2, we're going to fill the array up to n with the values, and then we'll return the final Fibonacci number that was calculated. Okay, submit this. Okay, 85% this time. And so in both the memoized strategy with the recursion method or the recursive method or this iterative method, we're going to be using now linear time complexity, because we'll calculate each fib of I up to n once. And then we'll also be using linear space because we'll have to store it up to n. Although, as a quick aside, because the numbers in the Fibonacci sequence get so large so quickly, it turns out that in reality, in practical terms, the space complexity is constant, because at n equals to 93, that's already the most 64-bit integer could store. So really, the best way would to, if you really needed access to Fibonacci numbers from 1 to 93, just store them in like a lookup table or something, and it'd be constant space. But anyway, I digress. Now we can actually improve this a little bit more. We can just use 2 variables instead. So why don't we do that? We'll need to add back our base cases though. Let's see, did I save it? Yes, I did. Okay, there we go. So save our base cases, and then no more array. We will now need n2. N2 will start at 0. This is, you can just think of this as the previous variable, the previous Fibonacci number. And then n1 will be equal to 1. And then we'll need a current variable. So for the current Fibonacci number, we'll return cur at the end. And then what are we doing in the loop? We're going to calculate the current Fibonacci number. How do we do that? Well, it's n minus 1 plus n minus 2, right? And then after we do that, we just need to move our pointers or move our variables. So the last term becomes the last term, and then n1 becomes the current term, right? And then we're going to calculate the next current term in the next loop, okay? So we can run this. Okay, and submit that. Okay, 88%, so slightly better. And this time, okay, it's still linear in terms of time complexity, but we're going to be using only 3 variables, so slightly better than, 93, I guess, right, at the upper limit. And the last thing that I'll say is there's also a explicit formula. This is known as Binet's formula, and this would calculate it slightly faster, but also doesn't really matter for small numbers of n. So with n less than, again, 93, the speeds will be the same. However, Binet's formula is the way to calculate Fibonacci for arbitrarily large values of n, and you do this by refactoring this equation. So this equation, as it is written here, isn't practically useful, but it is the basis for the derivation of a better formula. So if you were to use exponentiation by squaring, then the time complexity for arbitrarily large values of n, but you have to consider the constant time used for using a big int library, for instance. However, it is log n of the arithmetic operations. So it is interesting for, again, large values of n. But for now, we can just submit this as well. Just see what happens. 83%. So they're all about the same. Okay. Well, that is the solution to LeetCode 509 Fibonacci number. Subscribe to see more. We'll be doing the rest of the LeetCode 75 study plan questions in short order. Thank you, and see you next time.